Thank you, Yuri, for the introduction. So I will be speaking on behalf of the other co-authors of the chapter, in particular Christophe, Richard, Kevin, Cassandra, and Simone. And the underlined people here are the ones who are present at the conference. So if you have any further question that I won't be able to answer to, you can just stop one of us and have a chat about the topics of the talk. So we have heard already many both theoretical and observational talks yesterday and today that protoplanetary disks are rather complex dynamical systems. We have different physical mechanisms that are occurring over a range of different spatial scales. We go from turbulent motions to much larger scale magneto or hydrodynamical instabilities. We hope to have planet-disk interactions in these disks. We can have winds. We have tidal interactions with other stellar or substellar companions. And in general, we can have coherent gas flows, for example, from the gas falling from the disk surface onto the disk plane through like meridional flows. And so the questions that I'll try to start to tackle with this talk are, what are the main dynamical processes determining disk evolution and promoting planet formation? And can we detect signatures in current data of planet-disk interactions? And in order to do this, I will exploit the fantastic data that ALMA has been delivered in the last years in particular. And I'll be doing that with a kind of new methodology that has been developed in the last 5 years or so, which is really a new era of what we can do in terms of disk kinematics. So what are the typical velocities in disks? We have the dominant component, which is the Keplerian shear, and which is of the order of few kilometers per second. Another important parameter is, of course, the sound speed, which was instead of the order of about 300 meters per second for like a 25 Kelvin gas. We then have a line width, which can be affected by thermal broadening in principle, turbulent broadening, and even collisional broadening in the wings of the void profile, which is kind of somehow smaller than the sound speed, at least for like a CO molecule. And then we have a radial advection through accretion, which is a tiny fraction of the Keplerian speed. What ALMA can deliver today is an error mass of about 5 Kelvin over 150 meter per second channel at 0.1 arc-second resolution in about 10 hours of ALMA time. So the kind of spectral, which is incredible, resolution we can achieve today allow us to kind of look in spatial dependent information on these three velocity components of the disk dynamics. So how do we do that? First of all, let's take a step back. We've already seen a lot of beautiful maps in other talks, but if we look at a typical continuum structure of one of the very bright large disks in the sky, the gas emission is actually much more extended than that, at least in terms of the emission because of the high optical depth. And from these kind of maps, we can also retrieve a velocity map. So we can see how the gas is moving along the line of sight. This is a projected map. But how does this compare to the actual data that we get, which is a data cube? So if we image the gas line over a narrow channel bandwidth, what we get is the so-called channel map. And what is actually tracing is directly tracing the isovelocity contours of the underlying projected velocity field, exactly as it's shown in this animation. If we look at one of these single channels we already heard from by Ilse today, we can look at the disk structure. In particular, we can see the front and back side of the disk. I won't go into much detail about it, but it's very important to account for that to correctly deproject the data. And if we then take this one channel, we have the whole cube here, this the actual data we get on our computer after we reconstruct the images from the interferometric data. What we do get in reality is a line profile in every single pixel or beam in the map. So this line profile can be a composite of what is the back and front side of the disk. But if we focus on the main peaks, which are the front side of the disk, in most cases, we have three fundamental quantities that we can extract in terms of data analysis and then use to understand what's the underlying kinematical structure of the disk. The first one is, of course, the line centroid, for us the most important, which tells us how about the bulk gas motions at that specific location. We have a peak intensity, which is related to temperature and column density. And then we have a line width from which we can try constraining the thermal, in principle, collisional and turbulent broadening of the gas in a spatial dependent manner. So how do we do that? And that's something that is really new in the last 5 years in terms of how much we have pushed to develop this kind of methodology, and different teams have done independently in different parts of the world. So what we can do now is actually decompose the velocity field from the projected velocity into three orthogonal components, which are the azimuthal velocity, the radial velocity, and the vertical velocity of the disk when the data quality is good enough. And we can now do this with the outstanding precision of actually below 10 meters per second in the azimuthal and radial component and about 20 meters per second on the vertical one. So if we take any velocity we measure in any point of the disk, this is actually the composite of these three terms plus the systemic velocity. We can now extract what these three terms are. If we focus on the azimuthal component only, I will be talking a lot about this during the talk. This has a dominant factor, which is a stellar gravity, so the Keplerian velocity. But we actually have two other components, which are the pressure support, since we are talking about the collisional fluid here, and we have the self-gravity term. So here it's a sketch in terms of deviation from Keplerian rotation, showing how much these terms combine in getting different velocity, azimuthal velocity from Keplerian rotation. But the main point that I want to stress is that in case we have a substructure surface density, as in this plot that we're injecting in synthetic data, what we get is a substructured azimuthal velocity profile after we subtract the Keplerian shear. So we now have access to these two terms, pressure and self-gravity in principle. So how do we actually study these disks kinematically? There are two main methods. One is by looking at these velocity fields, which are derived by assuming that the disk is azimuthally symmetric. And the other method is just to look at the velocity map we extract in some way. I won't go into much detail about it. We have a model that we can, usually it's Keplerian, we can add the vertical structure, even the pressure if you want. And then we look at the residuals of this data minus model. And in this way, we do not have to make any assumption about the azimuthal symmetry, and we can look at how the disk is deviating from the expected Keplerian velocity in any point on the disk itself. So what was done before PP6? Mostly, but not only, the kinematics of disk was used with tremendous success to determine what are the dynamical masses of the central stars, which has been incredibly useful to actually benchmark primary sequence evolution tracks. And this has also now been expanded with AMA for about 100 disks so far. And he has it's potentially very powerful also for embedded sources where we struggle to get good spectroscopic data in the optical and near infrared. But let's take a step farther and let's start to look at what has been happening in the last 5 years. So what I'm showing here is the residual after subtracting Keplerian velocity of the azimuthal velocity field of one disk, MWC 480, as seen by 3 isotopologues. This kind of analysis has been done so far for 7 disks only. It requires really good data. And you can see that it's clearly substructured. So what we can do is, if we map that profile into 2D, as I'm doing here, you can then integrate it to directly get a pressure profile besides the normalization factor, and we directly measure the pressure profile as a function of radius of these systems. But if we also have some information about the temperature, which you directly get from the data, again, these are deviations from a smooth model, we can even go a step farther and try to constrain the radial profile of density along the emission where the line is tracing. And I think a fundamental result that is coming out, I mean, 2 of these papers have come out today. That's because this field is exponentially expanding, so it's really difficult to keep track of what's going on, is that at least 11 of the 13 continuum rings present in the map sample plus this object here are exactly coincident with pressure bumps. So we have the first clear observational evidence that pressure confinement of dust particle is a robust phenomenon and is causing the rings that we're seeing, or at least it coincides with rings present in the outer disk of these 6 systems. What else can we do with the pressure substructure? Going very quickly, I just will give some highlight of what we can do, and it's not exhaustive in any way. But what we can do is to compare the width of these pressure bumps with the width of the rings that Andrea has shown so clearly the other day. And this has to depend on the efficiency of radial trapping. So it will depend on how much diffusion of the dust counterbalances the actual radial drift towards the pressure maximum. And this is something that people have been doing. That's something we can now do observationally. And another thing which is about disk radia, we've heard quite a lot about it this morning, is that what we can also do is to look at the really outer edge of protoplanetary disk where the surface density is expected to fall off rather steeply. And in order to remove these huge dipole residuals from the map, what we need to do is to have this really steep tapering in the surface density. And we can have an idea of what the real outer radius is in terms of when the surface density really starts to drop off exponentially or rather rapidly. But let's look at another term. So we've looked at the stellar gravity, the pressure support. Let's look at the third one, which is the self-gravity term. So 3 disks have been analyzed so far, including this final term in the analysis by looking at the rotation curves. And 2 disks, 2 of them are with millimeter spirals. And the results are showing that we can actually get disk masses with this method, which is completely independent from anything we've heard about CO-based disk masses or continuum-based disk masses. These disks are fairly massive from this analysis, more than 10%, which is in agreement with the fact that they seem to be marginally gravitationally unstable. And a word of caution is that there is a tremendous amount of work being done right now to really characterize the systematics of this methodology, in particular how the pressure substructure will affect the mass estimates you can tease out. So we're talking about mass. Let's make another step. So we talk about self-gravity. What if the disks are gravitationally unstable? Can we see that from kinematic analysis? The answer is yes. And there are clear predictions that gravitational instability will cause distinct pattern in the channel maps where we get these S-like shaped, also called wiggles, that we can directly observe with good enough data. And this has been observed in LIS 227, which also shows spirals. So it is expected to be marginally gravitationally unstable. This is the only detection so far, which is surprising, I'm not sure. but what would be great is if we can move to earlier phases, in particular class 1, and see if this kind of phenomenon can be directly observed in more systems rather than just one. Let's make another step. So I focus mostly on the rotational, so on the azimuthal component of the velocity. What about radial and vertical? What I'm showing here, we have the height on the disk on the y-axis, the radius on the x-axis. And what we are showing here is the velocity field that we have directly retrieved from the data in R and Z. And the kind of length of the arrow tells you how quick, how fast the gas is moving for 3 CO isotopologues. And what we're starting to see are coherent gas motions that fall from the surface of the disk down towards the disk midplane. And these have been observed in this system outside the continuum edge. But there is also another surprise that has just come out, and that is actually in the gap seen in CO in the AOS 209 disk. There is clear evidence, and there are 2 independent papers that have shown it, that there is a clear, fairly fast, still subsonic, wind coming from the gap itself. So we have, for the first time, a coincidence of a localized wind with gas substructure seen in the intensity map. So the question is, also remembering what Mario told us this morning, is the wind generated by the gas substructure, or is the wind generating the gas substructure? And still, we don't know yet, but there are this is clearly discussed in particular in the first paper by Galloway's Prisma. Let's make another step, turbulence. So that's something that people have been trying to do already actually before PP6 by some pioneering work by Stéphane Guillotot. But what people do are trying to fit the channel maps, including a turbulent term, in the line profiles. And so far, 5 disks have been analyzed in detail because it requires expensive radiative transfer modeling to reproduce the data and to be sure to be treating the temperature quite correctly. And so far, there is one detection in the DM tau disk where the turbulent velocity is about 30% of the sound speed there. Another important caveat here is that, again, there are systematics here, and there is a lot of effort trying to understand what these are. And in particular, one is temperature itself and the ALMA spectral response function. Just another highlight is actually also local non-thermal broadening has been detected in a few objects, in particular in spirals, gaps, and clumps, but I won't give into much detail here. Let's make a further step into something Mario's already shown this morning, is that we do expect instabilities on large scale eddies, so in particular on H scale, to leave imprints in the kinematical pattern of the disk. And that's something we're possibly starting to see in some individual objects. And so this is promising in the sense that we do hope in the future to be able to characterize instabilities such as VSI and MRI on a large scale using this powerful kinematical method. But let's move to the final part of the results, of the highlights, which is planet-disk interaction. So I've heard that planets are extremely difficult to image through high contrast imaging, at least we're not finding many. What does kinematic tell us about it? So we expect embedded planets to leave a clear imprint in the disk, in particular through these spiral wakes that you see. But if we look at simulated observation by Seba Perez, and we look at what we expect to see, there are 2 main features. The first one is that you may expect a CPD to pop up where the planet is. But the second one, which is actually clearer, is that you see that this channel map presents this thunderbolt-like shape in the channel, which is in kinematical jargon, at least in the community, called kink. So azimuthally localized kinks may be able to trace the spiral wake of the planet. And the third tracer may be actually the Doppler flip that is expected, so red and blue, so Doppler flip, in the residuals maps. In general, there are several tracers. Some of them are localized, in particular the spiral wake. We expect to see the limbless spirals fairly clearly. Hopefully, there are other spirals, buoyancy spirals. I won't get into detail about it, but there is a whole class of mechanisms that are related and can be traced and can trace planet disk interaction in disks. So what are we seeing in the data? I think this is one of major revolution in our field, is that these kind of features are now starting to be detected in actual data. This is the first one that was clearly shown by Christophe Pinte. And you see this Thunderbolt-shaped kink, which forward modeling with hydro simulations show that the best explanation that this is tracing the spiral wake of the planet. And with the data quality, we're finding many of them in the data, but just be careful because only few of them are actually robust. And actually, if you look at this paper that was accepted 4 days before, July 11, 2013, then PP6 started, you can actually, if you squeeze your eye, you can actually see the kink present in those data already. So we had a kink already at PP6. We just didn't know it yet. What's interesting is that we do expect this kink to trace the spiral wake, and for this particular case, this is where the kink is. If we look at the residuals for this disk, what you actually see is a huge spiral wake trailing the disk itself. So this shows that the kinks are indeed related to spiral wakes. And another word of caution here, if you see a kink, it doesn't mean it's a planet, because different mechanisms that we already mentioned, like gravitational instability or VSI, do perturb your channel maps. So it doesn't mean if you see one that there is a planet straight ahead. You need to be careful and really forward model your data and show that you're actually tracing a spiral wake to be convinced to be tracing spiral planet disk interactions. Other methods have been used and are promising in the sense that we have candidate detections of planet disk interaction disk. One is the Doppler flip in this paper here by Simon and Seba. And another is a candidate circumplanetary disk emission in 13CO in the outer CO gap of AS209 by JMB. Again, several of these features have to be confirmed. Their interpretation needs to be verified, and there is a lot of work also on these two systems to try to understand what we're seeing. One final important bit is that the theory tells us that the amplitude in velocity of these perturbations, if we are below the thermal mass, has a clear, simple relation with the mass of the planet. If we know this h over r, so the thermal structure of the disk, quite well, and we measure a velocity perturbation that is related to a planet-disk interaction in a disk, we can measure the mass of the planets themselves. So this has caveats, but there is a huge amount of work also on the development of analytical theory that is very robust, and this is a clear output of any of these models. So we have, in principle, a method to measure planet masses if we believe that these are planets. Finally, the last slide before I move to the kind of concluding remarks is that there is also a huge development in the field to try to move from the kind of identification of these azimutally localized features just by eye scrolling through channel maps to actual clustering algorithms or machine learning techniques to infer the statistical significance of these azimutally localized perturbations. This has been done. It has already led to the inference of 3 localized features, possibly related to embedded protoplanets. And with this, we expect to reach a limit of about a Saturn mass planet, unless we have severe kinematical signatures from other mechanisms that are occurring in the same disk. But these are the kind of limits we have in the perfect disk. So what kind of planets we may be seeing with these methodologies? Here I'm just showing the usual plot, and here are all the disks from the dust substructure. Here we've added the two of what we think are the robust detections of planet disk interactions in HD 163 and HD 97048. And what you can see is that these are always above 1 Jupiter mass planet so far. And so with current, the level of data we have now, this seems to be where we are at. And of course, we are always very far out in the disk, and that's because we need the angular resolution or the linear resolution to scales to actually be able to see these planet disk interactions. What are the next steps at this point? So the first one are for ALMA. What I think we really need to do is to increase the statistics of kinematically characterized disks. We'll always be biased to bright disks with ALMA and large, and identify common fundamental dynamical properties of disks, and search for planet disk interactions in this larger sample, and try to quantify the insurgence of instabilities that can promote planet formation in the disk midplane. The second thing is to use different tracers, in particular thinking of ions and atomic carbon for different reasons, to map the full 3D kinematics of disk in a range of conditions. And with this, the ALMA wideband sensitivity upgrade will be great in terms of in the sense that we'll be able to cover many more lines in one shot. At some point, though, we'll always be limited by line sensitivity with the number of antennas we have now at ALMA. And finally, something that is kind of a dream is to, in a few years from now, even if this field is really at its infancy, is to go back to earlier sources where things are way more complex, since we have also the envelope, but to try to really understand the dynamical properties of disk in the earlier phase where they may be gravitationally unstable. And here, just to show something, to say that we have started to do this to try to increase the statistics at this new level of data. So here also no pictures and no Twitter, which are some preliminary images from the EXO-ALMA large program that we're conducting on 15 disks for 180 hours of ALMA time. And this is just one example of a channel map of one disk, image at 0.1 arcsecond resolution. Just trying to zoom for the people in the back, since you probably cannot see much. And the data quality is just exceptional. So it is worth it going for 10 hours on one disk to do kinematics. These are the continuum images of the disk we're getting. We're having 15, one we're still missing the data, and you see many familiar faces. But just to have a quick glance of what this 12CO peak intensity looks like, these are the images we are getting. So I will not go into any detail of what we're seeing or not seeing, but what you can see is the outstanding data quality, and that clearly substructures in the gas start to pop out very clearly. So to almost conclude, what are the next steps with other and synergetic instruments? I will talk mostly about observations and not about theory. There is a lot of development on that as well. The first one, which has come out many times, in particular today and yesterday, is to combine the kinematic results that we're getting and we will get in the next 5 to 10 years with ALMA with near and mid-infrared high contrast imaging campaigns with new or new generation instruments that are coming up. I'm thinking, of course, of JWST with NIRCam and MIRI, which will be tremendously useful in the very outer regions where we do not have much signal from the disk itself at these wavelengths. And it is going very deep. Some programs, both GEO and GTO programs, have been delivered. So we have the data in hand. And these high contrast imaging with JWST, they do go very deep at 2 and 4 micron, and with MIRI, we'll see the data when they come. And this has the huge potential, in my opinion, at some point to be able to, at least in a few cases, benchmark the mass luminosity relation of protoplanets if we have the mass from the kinematics and we have a good SED of the planets to be able to discern between the photosphere, CPD, and extinction, that we may be able to say how much energies these planets are retaining or freeing in the environment, and to understand how they are born and this large distance, which is still a puzzle for everyone, I believe. And these I'm just showing an example of a protoplanet candidate that I've seen in a poster here by Ian Hammond, where there is actually a kinematical counterpart that was already present in 2 previous papers by dependent groups. And another step, thinking about what to do before PP8. So we have another big eye that is coming along very soon, sooner than we will realize, which is the ELT. In particular, ELT METIS in the short mid-infrared will have the huge potential of doing this kind of analysis, but on smaller spatial scales in the inner 10 or 20 AU. So we'll be able to do the same of what we're doing with ALMA, but using, in particular, the CO fundamental line of 4.7 micron, using the mid-infrared. And that's coming very soon, before PP8. We should get ready for that as a community. So let me move to the conclusions. I've been extremely fast, faster than I thought. But what are the main points that I would like to have made during this talk? And the first one is that this field, which we call disk kinematics, had started before PP6, but has now, I think, exponentially exploded in the last 5 years and has a huge potential, but it's really at its infancy. So I'm sure it's a really fertile land for new discoveries in the next years. What we're seeing is that clearly for the disk where this analysis could be done is that they're largely substructure in their kinematical pattern, and we can understand and constrain physics of what's going on there. We have fairly clear initial evidence, even if recent, that pressure bumps are the main driver of millimeter rings in the outer disk for at least the 6 disks analyzed. Whoops. And we have potentially new way of estimating disk masses, at least for a subsample of our sources, which could be potentially very useful to benchmark independent methods and see how they correlate. For example, what Ilse mentioned this morning. And we do have convincing signatures, at least in a few cases, of Jupiter mass planet disk interactions ongoing in outer regions. And finally, what I'm fairly excited about, actually very excited about, is that if we will able, and if we'll see these planets with high contrast imaging in the near or mid-infrared, and we have a mass from the kinematics, we could really be able to understand how these planets may have formed by just looking at the planet mass luminosity relation directly from the data, which I know it sounds like a dream, but I think that we'll have these at least preliminary results about this fairly soon. And to conclude, this is just to say again that this field is at its very beginning, but it's very exciting, and so I'm sure that we'll have a kinematics chapter in PP8 as well. So I'll take any questions you may have on the topic. Thank you.
Yeah, thank you for a very comprehensive and very exciting summary of the data. Questions? So yeah.
Hello, what a fascinating talk. Congratulations. This is, I mean, it's really a new emerging field. Very impressive.
Thank you.
My question concerning the pressure bumps, you know, there always has been this discussion, how deep are these planet gaps that we see from the continuum concerning the gas? And now I think you can actually pin that down to pretty precise numbers. Yeah? So is is the gas following the dust, or is it only a small dip? Or when you say you can see these pressure bumps, can you also see how deep these gaps are?
So we could do it in principle. That's kind of a next step. So in terms of the pressure, we can do it straight away. In terms of the actual density, you need to know the temperature, just because what you're measuring is actually pressure. So we have an idea of it just by looking at the brightness temperature of the line, but that's what we're trying to do. So to have a good constraints on the temperature profile, we have the pressure profile to get the density. They do seem to be shallower, absolutely, than the dust itself, which is expected. But I cannot give you a quantitative answer now on top of my head. But that's something actually we should probably work on more as a community. But we have the data to do it.
Yeah, so there's related work by Christian Raab looking at the depth of these. When there would be completely empty, no gas at all, that would be actually too bright in the CO because you would see the other side shining through, and
yes,
that's not consistent with the data. So when you do this analysis, do you also have a look at the intensities?
So we always look at intensity as well when you're trying to get the density. When we look at pressure, what we try to do is to really distinguish the upper layer from the bottom layer. We have ways to do it because they would be actually separated in velocity, so you can distinguish them. So we try to get rid completely of the lower layer of the disk and just use the upper layer.
I am Sanichi Takahashi from Kagoshima University. Thank you, very interesting talk. I have a question about the way of the estimating of the disk mass. And in the equation, the effect of the magnetic field is not included. So my question is, how much affect the magnetic field on the estimation of the disk mass?
So my honest quick answer is that we haven't accounted for magnetic field affecting the rotation curve of the disk at all, but that's something we should do and will try to do. So that's a good point. Thank you for raising it up.
Thank you.
Hi, thank you for very nice talk, Stefano. I'm Tomohiro Yoshida from NOJ. Well, I have a question on the turbulent broadening of the line, the measurement of the turbulent broadening. In addition to the main factor that you said, main uncertainty factor that you said, I think the optical depth effect should be considered, because that if the line becomes optically thick, that can also broaden the line. Do you have a comment on that?
Yeah, so in these kind of models, then I recommend you talk to Kevin Flaherty, who's here in the room, is that's actually accounted for. So what they try to do is to actually feed the line through with radiated transfer models. They do account for the optical depth effects in the sense they do want to reproduce the saturated profile at the center. So that's accounted for. For dm tau, so far it seems that you still need an additional component, but that's something we'll keep looking into and trying to understand if there are other systematic effects that can play a role.
Okay, thank you.
Thank you.
This is Łukasz Tychańs from ISO. Thanks, Stefano, for great talk. I have a question regarding the degeneracies in those different parameters that can cause the kinematic signatures, especially the planets versus the disk wind. I haven't read the paper about the disk wind detection in the gap, but I was curious, what are the degeneracies there? And maybe related to that, would that be a limiting factor for detecting those features in younger sources, or are there Iono effects?
So, let's put it that way. I think that at the moment, from theoretical work, which I hope we'll keep developing in the coming years, driven by what we find or not find, is that the planet signature is fairly distinct from any other signature so far, in the sense that it's really azimuthally localized. And if you really trace the wake, and you can see that it's not a kind of a ring structure, but it's an actual spiral, that's really distinct. But the point is, which is a good one, that if you look at AS209, where we detected this wind, then if you look at the channel map, there are massive kinks, beautiful. So you say, hey, planets all over the place, but actually those kinks are generated by the wind. But if you look at the channel map, you see the kink all over the place. It's not at a specific azimuthal location. And that should start to warn you that what you're tracing is something that is more global. Concluding remark is that I agree, and that's an issue for younger sources, I believe, that if you have a very complex dynamics or kinematics for what you're tracing in the data, then it's very difficult to look for subtle deviation due to planets.
Connor Robinson, Amherst College. I just had a quick question. Are the disk masses that you're measuring through these methods consistent with what we're measuring through other ones? And do you have any advice on what we should be using for those?
They are consistent I believe that's Gemma Riga, which is actually one of the most difficult ones, but they're kind of consistent with what we're getting from CO disk masses, which is reassuring to me. And what's also intriguing is that if you look at the dust to gas ratio, just by using optically thin dust, with the masses we're getting, we get a factor of about 100. If you think about the uncertainty we have on both the gas and the dust, the fact that comes out 100 is actually scary because it sounds like magical. But at the moment, the self-gravity derived masses are in agreement with what we had from molecular tracers.
Hanpo Liu, Peking University. Thank you for the nice talk. Regarding substructure, the match in position between the gas pressure ring and the dust ring is very impressive. And now I was wondering, is it possible to infer observationally whether such depth trapping rings are in equilibrium? Or in other words, is it possible to compare and contrast the kinematics of the dust and the gas? Thank you.
So you mean if we have ways to check whether the dust is in equilibrium, if it's really trapped, or whether it's leaking through?
Yeah, so whether the dust is still being trapped in the ring, or
so what we can do, so there are, I think, two important ways two way forwards. One is to look, now that we have the kind of profile of the pressure bumps, if you compare it against multi-wavelength data by ALMA, we already know that the rings get narrower at longer wavelengths. There are also beautiful posters about it, also with the VLA. That's something that starts to tell you how efficient the trapping is. Whether there is a leakage term, so whether some of the mass goes through. So that's something we're actually trying to work on within the ExoAlma team. But I don't have a conclusive answer if that's something we really managed to do or not.
Thank you.
Thank you.
Thanks for a lovely talk. Richard Nelson, Queen Mary, University of London. So I'm just wondering about the two planets that you mentioned there, found through the velocity wiggles. Are they associated with known rings and gaps? And if so, can you also look at the global rotation profile of the disk and see whether it's consistent with also having rings and gaps at those locations in the way that you showed when you are using the radial pressure gradient to determine the rotation profile? So the most clear candidate, let's call it, we have is actually outside the continuum ring, which is also interesting. It's in a system called HD163296. It's about 230 EU, I believe. Another one is within a gap, which is the HD97048 system. The issue there is that the global kinematical pattern is difficult to constrain because we have self-absorption from an envelope or cloud on half of the disk, so we haven't managed to do this kind of analysis yet. But I know there is, I think, a group that now got much better data on it, so I hope they'll be able to. And to conclude, there is another planet candidate seen with this clustering algorithm. Again, is in HD163, that's within a gap found by Andres Izquierdo. And for that, we have a pressure profile. We haven't checked whether the mass we infer from the velocity perturbation matches with what we get from the pressure profile. That's something we should definitely do. So thank you.
Briefwaldsteck from Tautenburg, Germany. You mentioned that you have to have access to the outer regions of the disks because of the use of molecular lines in the submillimeter or millimeter, right? Would your method also be applicable to other emission lines, like the ubiquitous CO fundamental, to study the innermost disk regions in the same way?
So can you repeat the first part of the question again?
Well, the question is whether your method can be applied to emission lines at shorter wavelengths to study the innermost part of the disk.
Yeah, okay, so
like the CO fundamental, which is ubiquitous, shown by Webb.
Yeah, so that's something that we hope we can do in particular with METIS using the fundamental line at 4.7 micron. So these are simulated observations. These are not of planet-disk interaction simulations. This is just a disk with an injected planet. This is by Nick Oberg and Inga Kamp, who's here. And what they clearly show is that you would be able to detect the CPD if the planet is massive enough quite clearly with the 4.7 CO fundamental line. And by looking at the velocity resolution we have, we do hope that we can do the same kind of analysis we're doing now on the ALMA data with the CO fundamental line, but we still need to test this, and we want to do it before METIS comes online, which is fairly soon, and that's why I'm encouraging everyone, myself as well, when I find the time, to actually start looking into what's possible with the ELT.
Very promising, thanks.
Thank you.
Hi. Vlad Lyra, sorry, New Mexico State. Interesting talk. Thank you. What can I say? Like 10 meters per second. That's awesome. What I was wondering though is that you did mention rings and the spirals, but I noticed you didn't measure. You didn't mention the crescents, right? So I was wondering about them. If you could use this technique to try to measure the circulation and see if there is a vorticity associated with that, and prove or disprove if these crescents are vortices or not.
So that's a great point. So I didn't have the time to cover vortices. So what we will try to do, we know from synthetic observations that it's kind of hard, just because spatially these vortices are radially small. I mean, these crescents, let's call them, they're small, and therefore you need to have extremely good data to try to do it. What I can tell you is that we are trying to do it. Another thing you can think about is, rather than looking at the vorticity itself, if you look at how if you can try to infer a pressure gradient component along the azimuth, and that could tell you if there is a bump also in the gas density there. So that's a step before the vorticity, but that's something we're also trying to do. So I'll be able to answer you in a few months, but not right now.
Thank you.
Thanks.
Hi, Takeru Suzuki from University of Tokyo. My question is regarding localized winds from a CO gap. Is the signature of wind is only from less dense gap and no signature of denser ring region? Is it correct?
So your question is whether it's coming mostly from the gap and not from the ring?
Yeah. Less dense.
So what we're seeing is that most of the ring, the wind is really coming from the gap itself. I'm trying to find it here. So some of these emission that you see in 12CO, it's really at the edge of the gas starting to fall off. But most of this wind is really, really coming from the gap. Here it's indisputable, I would say. If you look at the residual map, you see this ring of blue shifted emission that is super neat. I don't have it here. And that coincides with the gap.
Okay.
And
Thank
the
you.
final question, Badir? Yes.
Thank you very much for the honor. Hubert Klar, Heidelberg. So, great talk. I wonder, we heard about this morning about vertical shear instability. So do you consider the vertical shear to model it, or can you even reconstruct it from your data, the height dependence dependent on temperature structure of the rotation profile?
So we hope to do, in the sense that what we hope to do is to really check in the data we have and the data that will come, whether we do see this kind of circular, structured, kind of large-scale eddies in the outer regions, which are consistent with VSI modeling. We use two different lines, which are tracing different altitudes. So in principle, we can trace whether there is a velocity dependence with height, whether we have enough statistics to see how this, if we see it, depends on disk properties. I don't think we're there yet.
I meant directly the rotation profile. So there should also be a difference in the Keplerian speed of 50 meters or 20
yes,
meters
that's
per
something
second.
good. Sorry, I misunderstood your question. I was thinking mostly about the radial and vertical. But that's something we are starting to look at. So there are differences already actually published. In some cases, I didn't go into detail, but if you look at some of this, you start to see differences between the CO isotopologues, and these are real. And these are at different heights in the disk. Whether these are caused just because you're tracing different pressures or different density layers, or whether this is related to some VSI, I don't know yet, but it would be great to chat about it. We need a lot of input from theorists to understand what we're seeing, because in many cases we have no clue.
Very good, thank you.
Thanks.
Okay, so we are running out of time, so please continue the discussion on Mattermost, and let's thank Stefano again.
Thank you.